Fred and Francine decide to go for a ride in hot air balloons. Francine forgets to bring extra propane. She has enough to lift up the hot air balloon, and that's all. But she thinks, that's okay, it just has to get up and then it'll float on its own. Fred brought extra propane. Who will go higher, Fred or Francine? Think about what's going on inside the hot air balloon. The hot air balloon is filled with particles moving in all different directions and very quickly. As we burn the propane underneath the hot air balloon, we're going to increase the temperature of the particles inside the hot air balloon. As we increase the temperature, the particles will move faster. This will increase the thermal energy of the particles. By increasing the temperature underneath the balloon, and as a result the air inside the balloon, we're increasing the thermal energy of the hot air balloon. The thermal energy is the energy associated with atoms and molecules that make up an object. In this case, it's the energy of the air inside the balloon. Let's consider this is an ideal gas, which isn't normally the case for a hot air balloon, but for analyzing it, we're going to consider this to be an ideal gas in here. And without bonds, the thermal energy of this ideal gas is equal to the total kinetic energy of the moving atoms inside the gas. When we heat the gas, it makes the atoms move faster, and it increases the thermal energy of the gas. It also increases the temperature. The temperature is a measure of the average kinetic energy of the gas. The thermal energy is the total kinetic energy of the atoms, and the temperature is the average kinetic energy of the atoms. The temperature is measured in either degrees Celsius or in Kelvin. Those are our SI units for temperature. And to convert between Celsius and Kelvin, we can use this equation. Temperature in Kelvin equals the temperature in Celsius plus 273. So if the temperature in Celsius was 0 degrees, the freezing point of water, the equivalent Kelvin temperature would be 0 degrees plus 273, or 273 Kelvin. The lowest possible temperature is absolute 0, and at that temperature everything stops moving. It's negative 273 degrees Celsius, or 0 Kelvin. Now we said that temperature was the average kinetic energy. So for a gas, we can also use this equation. This equation says the average kinetic energy of a gas equals 3/2 times this constant, the Boltzmann constant. The Boltzmann constant is equal to this value. You don't need to learn it. It is on your AP equation sheet. Times the temperature. Now the temperature must be given in Kelvin for this equation, and that's because the Boltzmann constant is given in joules per Kelvin. Also, the kinetic energy is going to be given in joules. Now we said that the temperature was the average kinetic energy of the particles in a system. We also said that thermal energy, and we're representing that with the letter U, thermal energy is equal to the total kinetic energy. We find the total by saying the number of atoms times average kinetic energy, and that will give us the thermal energy of the system. This equation is not on your AP equation sheet. If you increase the temperature, that increases the average kinetic energy, and if you increase the average kinetic energy, you've increased the thermal energy, so they're directly proportional to each other. Now in this case, we've put a flame underneath the hot air balloon. What that does is it causes the particles to move faster. We are using what is called heat. Heat is the energy transferred between two objects of different temperature. In this case, the heat would go from the flame, from the propane, and the energy would be transferred into the balloon. So let's think about what's going on in Francine's balloon. She has enough propane to take off. So she's increased the thermal energy of the balloon. The particles move more quickly. It actually is going to create more collisions with the edge of the balloon. More collisions means increased pressure inside the balloon compared to the air outside of the balloon. And we know that the pressure will move from an area of higher pressure to lower pressure. So the very hot particles, air particles, will stay in, but the cooler ones will come out the bottom. They will come out the bottom. So now we will have less mass per unit volume inside the balloon. And as a result, with a lower density, this balloon will rise up into the air. But after a certain amount of time, what's going to happen? When the air particle collides with the wall, it's actually going to transfer its energy through the edge of the balloon. And an air particle on the outside is going to speed up and absorb some of that energy. As a result, this air particle will lose energy and slow down. Anytime there's a collision with the wall, energy will be transferred outside of the balloon. So what's the result on the inside? The particles will slow down. The particles slow down, the average kinetic energy decreases, and the temperature will decrease inside the balloon. So what will happen here is the thermal energy moves from areas with the higher temperature to areas with the lower temperature until the system reaches thermal equilibrium. And thermal equilibrium is when both systems are at the same temperature. So over time, the extra temperature, the higher temperature here will no longer be higher than the outside. Those two temperatures will become equal. When that happens, Francine won't be able, she will actually go back down to the ground again. So if she didn't bring any extra fuel, she can't continue to heat this balloon. All this energy that she has put into it will be lost to the air around the balloon, and her balloon will fall back down. So the answer, who will go higher, Francine or Fred? Well, Fred has a continuous supply of propane. He can continue to heat his balloon, and so even though some of the thermal energy gets lost, he'll continue to add more heat, and he will be able to fly higher than Francine. The definition of thermal expansion talks about a solid. When a solid is heated, molecules move faster and volume expands. But it's also true for the hot air balloon. When we heat the air inside, they move faster, and the volume would like to expand. However, the balloon is strong enough to keep it from expanding. So what ends up happening is the cooler air will come out the bottom so that it doesn't. So the overall volume taken up by the air is bigger. It's just outside of the balloon for part of the air. If you think about if you have a jar of tomato sauce and the top is stuck, you want to loosen the top, but because of the very low pressure inside the jar, it's much harder to open the top. So to open the top, we run hot water over the top of it from the sink. That hot water will allow this metal top of the jar to expand, and it will loosen the jar for you. Now Fred and Francine are going to take another air balloon trip. This time Francine knows to bring enough fuel. However, Fred has done something different. He's decided to use a smaller balloon. So the question is, will it make a difference? Who goes higher? Fred thinks that because he has a smaller balloon, it weighs less, and that less weight will allow him to go higher. The forces acting on a balloon in the air are the force of weight, and the buoyant force. The buoyant force is what allows a hot air balloon to go up. Well, what is the buoyant force equal to? The weight won't change. Well, Fred's is slightly less than Francine's. So the actual weight difference is going to not make that much of a difference in this case. What makes a bigger difference is the volume of displaced air. As you go up in altitude, the density of the air decreases. As the density goes down, the buoyant force goes down. But if you have a large enough volume, you can still go up in the air, and gravity will be the same for both of them. So the larger volume of displaced air is the balloon that will go higher.